In this problem, I will use dimensional analysis to convert two rates. We are taking care of a client who starts to experience frequent ventricular dysrhythmias. The physician orders an infusion of lidocaine within a range of 2 to 4 milligrams every minute. We know the drug is available 2 grams every 250 milliliters. The first thing we need to do is to convert our minimum dose of 2 milligrams. So if we look at part A, we need to take the 2 milligrams per minute and we need to convert that so that we have milliliters per hour. I'm going to use dimensional analysis because I can see that this is going to have multiple steps. I see that I need to convert milligrams into milliliters, and I need to convert minutes into a unit of hours. Since the units of minutes to hours is a little bit easier, I'm going to start there. I'm first going to eliminate minutes by writing a unit of minutes in the numerator of the next conversion factor. So if I want to convert minutes, it needs to be in the numerator of the next factor that I multiply by. I want to go from minutes into hours, so that will be in the denominator. I know 1 hour is equivalent to 60 minutes. Right now, if I were to stop, I would have the total number of milligrams the patient should receive every hour. Since I have hour, which is what I want at the end, I'm going to circle that. I do not want to change that. In order to convert milligrams into milliliters, I need to consider the medication that's available. If I look up top, I see what's available is 2 grams for every 250 milliliters. This is telling me that if I want to convert into milliliters, I would need to have a measure of grams. But since I have milligrams, it looks like that's going to have to be my next step, is to take milligrams and convert it into grams. Now I'm going to include it in the dimensional analysis because that's why dimensional analysis is great. It allows us to have conversions built into the problem. Some students may take this 2 grams and just on the side maybe write 2,000 milligrams in 250 milliliters. So if you have a good understanding of the metric system, then maybe on the side you just want to rewrite this as milligrams 250 milliliters and use that down here. But instead, I'm going to just convert first into grams, and now that I have grams, I'm going to use what's available, 2 grams in 250 milliliters. Both of these approaches would arrive at the same conclusion. I now have my milliliters, so let's see what we get. If you multiply the numerators here, 2 times 60 times 250, 2 times 60 times 250, you get 30,000. And if you look at the denominators, I have 1 times 1,000 times 2. This is going to be 2,000. It should be pretty clear that our simplified version here, if we were to take 30,000 divided by 2,000, what we get would be 15. So this would be 15 milliliters per hour. That would be the minimum dose. Now, we need to look at part B. What is the milliliter per hour rate for the highest dose? Looking at the order here of 2 to 4 milligrams per minute, it looks like, and actually it is, the maximum dose is twice that of the minimum dose. So if I had to guess, my guess would be if I wanted the patient receiving twice as much, I'm probably going to increase the speed by 2. So just a quick thought over here on the side, I wonder if this is going to be doubled to 30 milliliters per hour. That's my thought. Now let's do the same dimensional analysis approach that we used up above, but instead of 2 milligrams, let's start with 4. So now we're looking at 4 milligrams per minute. You're going to notice that the steps are going to be exact. We want to cancel out minutes, so I will multiply by 60 over 1. That changes the unit of the denominator to hours. So 1,000 milligrams into grams, so 1 gram. And if I do that, milligrams cancels, I get grams. Now I want to go into, oops, I don't want to circle that. I want to cancel out grams and go into milliliters, just going through the steps here. I know what's available is 2 grams and 250 milliliters. And now I want to circle because I'm done. I have a unit of milliliters up top. If you multiply 4 times 60 times 250, what you'll get is 60,000. And down below, if you take 1 times 1,000 times 2, you will once again get 2,000. If you simplify this, you're going to get 30, and it'll be milliliters per hour. So it looks like my thought that it would double was correct. And if you look at the work, you can see why that's true. The only difference between the first dimensional analysis work and the second work is that I started not with 2 as I did in part A, but I started with 4 milligrams. All the other steps, multiply by 60 times 1 over 1,000 times 250 over 2, all of those 3 steps there are exactly the same, which means all I'm doing is starting with a number that's twice as large as I started with, which means my answer will be twice as large.